progress.
All right, oops. So again, I'm Michael Pfeiffer. I have a bachelor's and master's in metallurgical engineering, and I have a PhD in material science and engineering, and I've been working over 25 years working with design and manufacturing companies to help them with metals engineering, helping with product design, manufacturing, quality improvement, and also failure analysis and root cause analysis when there are problems. So today I'll be talking about common causes of product delays and how to prevent the product delays. And I'm going to be giving the materials engineering perspective, which I think for a lot of people is a unique perspective. It's in many cases, it's principles that people are completely unaware of. So there are four common causes of delays and where materials engineering fits in. So there's product test failures, component fabrication problems, incapable suppliers, and manufacturing processes that are not production ready. So these common problems occur that can increase the likelihood of delays, and often organizations think these delays are a fact of life, and they really don't have to be. We can do things to prevent these delays from occurring. So the first thing is product test failures. This is when the materials in a product are unable to withstand exposure to the test conditions. It might be corrosion conditions, vibration, high temperature exposure, whatever it might be. Regardless, the product is unable to pass the testing because the materials in the components in the product degrade too much and components fail. And so what has to happen next is that the design team needs to do a root cause analysis on the components that failed. They have to identify a fix, put that fix in place, and then they have to go about and repeat the testing. A lot of organizations, they're hopeful that they're going to pass the testing the first time, and they will often develop their timelines based on passing the testing the first time. And when there are problems, then that upsets the schedule. The root cause is poor material selection. They selected materials that were not capable of withstanding exposure to the use conditions. So the way to pass product testing the first time is to identify potential materials up front, test them prior to product testing, and use the evaluation data to select suitable materials that are going to be able to withstand exposure to the use conditions. So there are four steps to this. There's, first of all, identifying the component's design requirements, thinking about all the things that the components have to satisfy. Performance requirements, reliability requirements, and reliability means understanding what the application exposure conditions will be, as well as what the test conditions exposure will be. Also, fabrication requirements and cost and other requirements. And based on these requirements and having a complete set of requirements, we can then identify potential materials that meet these requirements and ideally at low cost. And we also want to be thinking about design for manufacturing and design for reliability. For the purposes of this slide, I'm concerned about design for reliability. Identifying materials that have the likelihood of being able to withstand exposure to the use conditions without degrading to the point where the components fail. The next step is to do materials level reliability testing. This means getting samples of the materials and exposing them to the test conditions. So we don't have to build the entire product. We can just evaluate the materials and understand how they degrade during the use conditions, and also how their properties change due to exposure to the use conditions. Materials might degrade a little bit, but as long as they don't degrade to the point of failing, that'll be okay. And this is done in parallel with other design efforts, and the information is then used for the design team to select a suitable material. Now we might not want to do this for all the components in a product. We might want to select components that are strategic, or that are going to be, we feel, have the most aggressive conditions exposed to them, or components where we think that there have been increases in the exposure to whatever conditions are that the material is being exposed to. The conditions are more aggressive than previous products, and might think that you have to go to a different material because the old material that had been used in past products wasn't going to work out. So you might not, again, do this process for every single material in a product, just for critical components. But the point is that by collecting the information, we can identify materials that can pass reliability testing on the first time, so that when you put a product through testing, you have a much greater confidence of passing the full product testing the first time. The second thing that can cause delays is component fabrication problems. And this is fabrication problems due to difficulty with your component fabricator meeting your specifications. It means they're having problems meeting dimension requirements, shape requirements. Maybe the materials don't have the right properties afterwards, or manufacturing defects. This could be machining or injection molding or casting or extruding, whatever it might be. But they're not a bad supplier. They're a good supplier, but there are problems with the design of the component. The materials that have been selected are problematic, or the tolerances are too tight, or there's the incompatibility between the shape of the component and the process that's being used. So the root cause is that there's no design for manufacturing considerations during component design, and as a result, you have problems. The supplier has problems making the components or making the assembly that they're trying to make for you. So the way to avoid this is to consider design for manufacturing and assembly during design. This means selecting materials that are easy to use in the process, coming up with shape and features and tolerances that are compatible with the process. You don't want to design a component that has a certain shape and try to die cast it and find that it's difficult to eject from the die casting mold because it's not shaped for good ejection from the mold. And the same thing for injection molding of a plastic part. So are the materials compatible with the fabrication and assembly process? So for example, 303 stainless steel is easier to machine than 304 stainless steel. So if you're going to be making 500 parts of something, maybe 304 is okay. But if you're going to be making 5,000 parts of something a week, then 303 stainless may be the way to go, because we can machine 303 stainless much faster than 304. However, there's a trade-off, because 303 stainless steel has slightly less corrosion resistance compared to 304. Or it could be welding two steel tubings or rod together. Plain carbon steel is going to be easier to weld than low alloy steel of the same carbon content. So we have to be careful to select the steel composition that will be easy to form weld joints, and make sure you don't select a steel that will require extra babysitting or extra steps in order to form good weld joints, because that can slow down the welding process and also increase the cost to make the weld joints, and which then results in increased cost to you. And then, are the shapes and features and tolerances achievable with the process? So the thing I recommend is you talk to your fabricators and also get materials engineering input. Find out are there materials that you've selected appropriate for the application and for the process, and are the shapes, features, and tolerances really achievable? The third cause of delays is having incapable suppliers. This is when you find a low-cost supplier and you bring them on and they're unable to consistently meet your specifications. This can be for stock materials such as metal sheet and coil and bar, plastic pellets, metal powder, tubing, also fabricated components like castings, injection molded parts, extruded parts, and so on. So their supplier is unable to meet your requirements for the material properties or the composition or manufacturing defects or component dimensions and shape. And the root cause is insufficient due diligence, not doing a good enough job for evaluating the supplier to make sure that they're capable of providing materials or components that can consistently meet your requirements. So the first thing to do is you want to make sure you're selecting capable suppliers, and the first thing to do is to write a thorough and accurate material specifications. I see so many material specifications that are missing information, and the problem with that is then you're not communicating to your suppliers what you expect from them, and also they're not understanding what the expectations are of them as well. So you want to make sure you're communicating the expectations, and you also want to get feedback from the suppliers. Do they understand the expectations? Do they think they're capable of meeting those expectations, and have them explain why? The second step is to analyze the samples from suppliers. Get a sample of production materials from the supplier and evaluate them. This could be either the stock materials or components that are already in production with them, or you can have them make some components for you for evaluation. Do the samples have the proper composition and microstructure and properties and acceptable level of defects? Do they have the right tolerances and shape? So for example, shown here are micrographs of gears from two different components. So a client was looking to go to a lower cost supplier of gears that were heat treated, and the purpose of the heat treatment was to form a hard case on the teeth of the gears and leave the rest of the gear unaffected. Well, they wanted to get 9 thousandths case depth. That means a 9 thousandths thick hardened layer, and they went to they got a sample from a lower cost supplier, and they had a much thicker case depth, much thicker hardened layer, which is actually problematic. That's not a good thing. So now the client had a decision to make. Did they want to continue on with this low cost supplier? It was going to mean investing some time in bringing them up in terms of their quality, or should they just move on to another supplier? But at least they had the information, and the cost of doing the analysis was about $2,000. So small cost to avoid working with a problematic supplier. The next step, after you've determined that a supplier can make something that's going to meet your requirements, is to evaluate their production capabilities, quality systems, and technical knowledge. Basically, do they have the ability to control their processes, and do they have the ability to quickly solve problems? Problems are going to arise. You just want to know, do they have the technical knowledge to quickly address those problems and fix them so that they're able to continuously send you parts and materials that you can use in your production line so that you can meet your schedules. You don't want to delay your product because of problems with your suppliers. The final reason for delayed products is manufacturing processes that are not production ready. You have quality problems, there's scrap and rework and low throughput. And this could be because of problems with component shape and dimensions and appearance, or problems with an assembly that's being produced. Material properties aren't what they need to be. Joint shape and strength are not good, and there's excessive defects in the components or in the assembly. And the result is again scrap and rework and low throughput and delays to shipping your product. And the root cause is insufficient process characterization. And again, through materials engineering, this can be avoided. So we want to develop production-ready manufacturing processes, which means characterizing the effects of the process inputs and process conditions on the output. So the process inputs are the materials that are going in. They're understanding what are the properties of the materials that are needed, what does a microstructure is needed, what is the maximum, what types of defects are allowable, and what's the maximum amount of the defects that are allowable. Also the process conditions, understanding their effects on the materials. How do they affect the material properties and the defects? So for example, consider someone purchasing steel wire and steel tubing, and they're going to cut wire and cut tubing into a certain shape, and they're going to weld them together, and they want to have weld joints that have good strength, and they want to make sure that the wire components and the tubing components have the right shape, and that the assembly is a good assembly. Well, having a good material specification and understanding what defects are allowed in the material, the required composition, the required microstructure in the materials they're going to purchase, and then characterizing the effects of the welding process on the weld joint, and measuring the weld strength and looking at the weld microstructure so that we understand the effects of the input materials and the welding process on the final assembly and on the quality of the final assembly. And if you're going to be making thousands of weld joints a day, you have to have this information so that you can continually make thousands of weld joints a day and be confident that all those weld joints are going to be good. So we want to identify the input material requirements and the process conditions that result in a capable process. So in all these cases, for these product delays, what's missing is materials engineering expertise and perspective. So there should be no surprise. That's kind of the punchline of this presentation. And to me, if you look at any product, it consists of ultimately a bunch of different components that are engineered, and the materials are engineered, and the materials are shaped and modified and brought together to make the product. And we can engineer the materials and engineer the processes so that we get materials that meet requirements and get joints that meet requirements so that the components and the product meet the performance, reliability, and cost requirements. So selecting the materials is a critical part. We want to optimize performance, reliability, and cost. And the other thing is controlling the materials to meet the requirements. Writing good material specifications, having a solid supplier selection process, developing capable manufacturing and assembly processes that are able to continually produce components and joints that meet requirements, and having a disciplined, focused root cause analysis process. And that means being able to evaluate the materials when there are problems and understand the metallurgical reasons for the problems or the materials engineering reasons for the problems, and then using that information to determine the root cause of the problem. And then from that, putting fixes in place to prevent the problem from occurring. So there are two takeaways. The first is that product delays don't have to be a fact of life. There are a lot of things that can be done to prevent product delays from occurring, at least from the materials engineering perspective. And the second, that we can apply materials engineering to design and manufacturing decisions to improve the likelihood of success and develop products that we can make over and over again and not have delays, be able to meet schedules, and have good quality. So that is it. So now I'll take your questions. So that was about 20 minutes long. So do you have any questions? If you have questions, I can either unmute you or you can type your question into the chat box. Do you have a specific question or a question about the process that I discussed? No questions? Okay, well, if there, well, I'll keep going then. If you have a question, just type it in, or you can also click the raise hand thing, and I can unmute you if you want. So, for those of you who are interested, there are some steps if you want to look into materials engineering more for helping to avoid product delays. You can learn how materials can be engineered. There are lots of courses online, and also you can get on site and through different organizations about the science and engineering of materials. We also offer courses on metals and how metals can be engineered, or how metals are engineered, and also on failure analysis and on corrosion and other aspects of metallurgy. Also get training to learn the details of material selection and supplier selection and process development. The thing is, I think a lot of organizations expect mechanical engineers to be materials engineers, and these organizations have very skilled mechanical engineers, and they're very smart people, but they're not materials engineers. And expecting them to be is probably unrealistic for management, and even for the people who are trying to do it. Trying to act as materials engineers. So get training to learn the details to become more knowledgeable about the engineering of materials. And finally, I can meet with you to discuss specific problems if you want to set up a time to meet. So if there's no questions, here's my contact information. More information about the things I discussed are on the website. There's articles, there's web pages about it, and also videos. And if you'd like to set up a time to talk, here's my contact information is there as well. If you also, a very brief survey will launch when you're done. If you take a moment to complete it, that'd be great. So a question is, I have here is, how do you help convince senior management that working with a quality supplier is worth the extra cost when the product is not released? Meaning it is easy to see failure rates of the currently released product, but new release is hard to predict failure rates. I guess you have to go look back at old products and see and document what the failure rate or what any delays that occurred with old products and what the costs were with previous products. And if you can document that, maybe you can demonstrate how the cost of working with a quality supplier and also demonstrating that a low-cost supplier is really not going to be so low cost is worth the extra, is worth the investment. So basically you have two choices. A company can either invest in preventing a problem, or they can spend the money on fixing problems. Those are the choices. And people are very hopeful, and they always think, well, next time it's going to be different. Well, why is it going to be different? What are you doing that's any different? And if management is not innovative and open to doing things differently, then you're kind of stuck, unless you can put together the data to demonstrate what happened in the past and what can be done to prevent it in the future. So, and being able to document the costs of delays. It's not only the cost of scrap, but it's also what did it cost in terms of delaying shipments to your customer, in terms of missed sales, as well as reputation, and maybe a customer decided not to come back to you again for future business. Okay. So someone says, could you explain your approach to the material selection criteria? So when designing a component, we have to think about all the different requirements that are going to be on the component. So there's the performance requirements. There's going to be mechanical or electrical requirements. Also, there might be weight requirements as well. And there's going to maybe appearance, and of course cost. Then there's also going to be requirements on the reliability of the component. So what are the use conditions? Will it be exposed to corrosion conditions, or fatigue, or wear, or creep, or anything else that will cause degradation of the materials? So we have to identify those, all the reliability requirements. Then we also have to identify the fabrication components, fabrication requirements, and assembly and joining requirements. So what process are you considering using to make this component? If it's going to be forged, then there might be certain materials that you can use. If it's going to be extruded, there might be other materials that can be used that are suitable for that process. Same as with machining. And also with joining. Some materials are easier to join with welding or with soldering or brazing than other materials. So you have to identify those requirements as well. So coming up with a complete list of requirements at the beginning is important. And then based on those requirements, we can then identify what materials meet all those requirements. And sometimes we may be identifying, we're not 100% sure about materials, we're identifying potential materials. Also, by going through this process, you might identify a material that you're very confident in can meet the requirements, but also there might be a material that gives you a competitive advantage. Maybe it gives you a cost advantage by using a different material, or a material with a certain coating, but there's more uncertainty about that material. But if that material works out, and we can evaluate the material, and if it determines that material works out, then that can give an advantage with cost, or maybe it has better performance abilities or better reliability. So anyhow, we identify the potential materials, and then from there go on to testing the materials and evaluating them. And then by the time, then use that information to help the designers then select the final material. So this is a discussion between materials engineers and design engineers, and also maybe with the fabricators or assembly people as well. So that's the basic material selection approach. Okay. All right, well, it looks like there's no more questions. Thanks again for attending. And again, please complete the survey, and good luck with your materials and metals going forward. Bye.